Vision transformers have fundamentally changed how we approach image recognition, but they still struggle with two persistent issues: the quadratic computational cost of global self-attention and a lack of an inherent spatial prior. While standard ViTs treat every token pair equally regardless of distance, relying entirely on learned position embeddings, newer architectures have tried to bake locality directly into the math. Today, we're diving into a new research paper that proposes a sophisticated hybrid approach called Gated-SwinRMT. This architecture unifies the shifted window mechanism of the Swin transformer with the Manhattan distance spatial decay found in retentive networks, all while introducing input-dependent gating to solve a specific problem known as the Windowed-Softmax Pathology. To understand Gated-SwinRMT, we first have to look at the two pillars it's built upon. First, the Swin transformer. Swin solved the efficiency problem by confining attention to non-overlapping windows and alternating between regular and shifted partitions. This allows information to propagate across window boundaries while keeping complexity linear. However, Swin relies on learned relative position biases. It doesn't have a principled, distance-weighted decay modulating the attention weights. That's where RMT, or Retentive Networks for Vision, comes in. RMT introduces Manhattan self-attention, which multiplies attention scores by an exponential decay based on the Manhattan distance between tokens. To keep this efficient, RMT decomposes 2D attention into sequential 1D passes, first width-wise, then height-wise. The authors of this paper noticed that when you combine these two, Swin's windowing and RMT's decay, you run into a major problem: the Windowed-Softmax pathology. Here is the technical breakdown. Softmax forces attention weights to sum to 1 within every window. This means the model is compelled to attend to something in every local neighborhood, even if that neighborhood contains no useful information. In a global attention setting, this is fine because the weight can redistribute across the entire image. But inside a small, fixed window, the model is forced to assign weight to noise. The researchers found that this causes a significant performance drop when moving from low-resolution images, like CIFAR10, to higher-resolution images like Mini-ImageNet, where the windows are actually subsections of the feature map. To fix this, the authors propose two distinct variants: Gated-SwinRMT Retention and Gated-SwinRMT SWAT. Let's start with the retention variant. This version keeps the softmax normalization, but fixes how the spatial decay is applied. A common mistake in these architectures is applying multiplicative decay after the softmax, which violates row stochasticity and leads to gradient instability. Instead, Gated-SwinRMT Retention uses an additive log space decay bias, similar to a-Levi, applied before the softmax. To solve the softmax pathology, they introduce a G1 sigmoid gate. This gate is projected from the block input and applied after a local context enhancement module, which is essentially a 5x5 depthwise convolution, but before the final output projection. This allows the model to independently suppress the output of an entire head if the retrieved content is uninformative, effectively breaking the low-rank bottleneck of the value output projection. Then there is the SWAT variant, which takes a more radical approach. Instead of softmax, SWAT uses a normalized sigmoid activation. Because sigmoid outputs aren't required to sum to 1, the model can simply ignore uninformative tokens without being forced to distribute weight. SWAT also implements balanced a-Levi slopes, where half the heads have negative slopes and half have positive slopes. This ensures the positional prior doesn't accidentally favor one spatial direction over another. Furthermore, it replaces the standard value projection with a SWI-glue transform, which enriches the value representation with a data-dependent gating signal before the attention operation even happens. One of the most practical additions here is adaptive window sizing. In deep networks, by the time you reach the final stages, your feature map might be smaller than your intended window size. Instead of letting the model crash or using clunky if-else logic, Gated-SwinRMT dynamically clamps the window size to the feature map size. If the feature map is 2x2, the window becomes 2x2, and the model gracefully degrades from windowed attention back to global attention. So how did this perform? The results on Mini-ImageNet are compelling. The SWAT variant achieved an 80.22% top 1 accuracy, and the retention variant hit 78.2%. Compare that to the baseline RMT, which sat at 73.74%. That is a massive jump of over 6 percentage points. But the most interesting data comes from the CIFAR10 tests. On CIFAR10, the images are so small that the adaptive windowing essentially turns the model into a global attention network. In this bypass regime, the performance gap between the new variants and the baseline almost disappears, shrinking to just 0.56%. This is the smoking gun for the researchers. It proves that the G1 gate and the sigmoid normalization aren't just general improvements. They are specifically solving the problem of forced attention within small windows. When the windows disappear, the advantage disappears. In terms of efficiency, these additions do add a bit of overhead, roughly 20 to 24% per epoch on Mini-ImageNet, due to the depthwise convolutions and the expanded projection dimensions for the gating. However, the trade-off in accuracy is significant. To summarize, Gated-SwinRMT shows us that the sum-to-1 constraint of softmax can be a liability in windowed vision transformers. By combining the spatial priors of RetNet, the efficiency of Swin, and the flexibility of input-dependent gating, we can create a backbone that is both spatially aware and capable of ignoring the noise. While the authors note that future work is needed to test this on full-scale ImageNet 1K and dense prediction tasks like segmentation, this research provides a clear path forward for making window detection more robust and expressive.